Welcome back to Science Modernizers, welcome back to our channel, and welcome to the Science Modernizers e-learning platform. In today's video, we are going to solve some questions in Physics Paper 2, that's the Cameroon GCE, the Cameroon General Certificate of Education Board, Paper 2 type. So, we are going to be solving physics questions. Dimensional analysis. So more particularly, we are going to solve GCE questions. So let's see, we are going to solve the Cameroon General Certificate of Education Board past questions. Okay, so now with this we can begin our session. Now we are going to begin with June 2017, the very first question. It says the energy stored in an airfield's parallel plate capacitor whose area of overlap is A and is given by the equation E is equal to V squared A epsilon naught divided by 2D, where D is the separation between the plates, V is the potential difference across the plate, and epsilon naught is the permittivity of free space. Show that this equation is homogeneous. In order for us to show that the equation is homogeneous, it suffices for us to show that the units of the left hand side is equal to the units of the right hand side. So then, how do we proceed? So we identify that our equation E is equal to V squared A epsilon naught, all of this divided by 2D. So this is the right hand side, so that's the right hand, sorry, this is the left hand side, and this other side is the right hand side. So in order for this equation to be homogeneous, the units of the energy E should be the same as the units of this quantity V squared A epsilon naught divided by 2D. Now we have to notice that the units of dimensionless constants such as 2 is 1, so they are all unitless. So in dimensional analysis, these constants do not count, so you can consider them as non-existent on this equation. So they are actually here to define the correctness of that equation. Okay, so we are going to begin with the base unit of E. Now E is energy, and in order for us to get the units of energy, trying to check any relationship which links or which you can use in calculating energy. There are several forms of energy: mechanical energy, kinetic energy, potential energy, etc. And so energy can also be stored in the form of energy, can also be in the form of work done, since work is a form of energy. And so work is the force times the distance moved in the direction of the force. Also, I like using this because it is very simple to come up with the units of energy. Now you can also use energy in the form of a kinetic energy, which is a half mv squared. You can also use it in the form of potential energy, which is mgh. So no matter the value, no matter the formula which you use, you can still use E equal to mc squared. So no matter what you use, at the end of the day, we just have to derive the base unit of the quantity joule, of the joule. So this is force is, from Newton's second law, is the mass times acceleration times the distance d. So energy is mass. And so what are the base units of E, of m? The base unit of m, where m is the mass, is the kilogram. The base unit of acceleration is the meters per second square, times the base unit of distance, which is the meters. And so meters times meters gives meters squared. So we have kilogram meter squared per second squared. So these are the units of the left hand side of the equation. So how do we report this? Let's report this on one side. Hence, units of E will simply be the kilogram. Let's get space. So the units of E will simply be the kilogram meter squared per second square. So let's note this. Now we are going to verify the units of the right hand side, but always know what the quantities define. So let's begin with easy quantities like d, which is the separation. So let's start with the units of d. So now we are verifying the units of the right hand side. So what is the unit of d? So unit of d. So since d in separation, the base unit is the meter. Now the next is A, which is the area of overlap. So units of A. Area is the measure of the length and the width, so it's given by meter squared. The next quantity is epsilon naught and v squared. Now v squared is the potential, or v is the potential difference across the plates of the capacitor. And so what we get is, we have to get the base units of V. Now the potential V is simply given by the work done per unit charge. And we already saw the units, the base unit of work done, in other words the base unit of energy above, which is the kilogram meter squared per second square. All of this divided by the unit of charge. From Faraday's, charge is equal to IT, where I is the current, so that's the ampere, and the unit of time is seconds, and so we can replace by ampere seconds. And so this simplifies to give the kilogram meter squared per second squared. All of this, the amperes goes above and the second goes above, so I get per second per ampere. And so this gives the kilogram meter squared per second cube amperes to the negative 1. Now, but we are not interested in the unit of V, we are interested in the unit of V square. So let's get the unit of V square. So the unit of V square will simply be kilogram meter square seconds to the negative 3 amperes to the negative 1, all of this squared. So which is going to give the kilogram squared meters to the 4 seconds to the negative 6 amperes to the negative 2. So that's what we get for the unit of V square. Now let's get the unit of epsilon naught. Now epsilon naught is the permittivity in free space. Now we are evaluating the units of epsilon naught, which is the permeability in free space. So we can use the Coulomb's law of electrostatics, which says the force between two charges is given by the product of the charges Q1 times Q2 divided by 4 pi epsilon 0 r squared, where r squared is the separation between the two charges. And so making epsilon naught the subject, we get that epsilon naught will be Q1 times Q2, all of this divided by 4 pi f r squared. But 4 pi is a dimensionless constant, and so we get the unit of E, the unit of epsilon naught, to be equal to the units of charge as seen above from Faraday's law is the ampere second. As seen above, as seen here, is the ampere second. So since it's charge times charge, we are going to have ampere second, all of this squared. This will be divided by 4 pi is a dimensionless constant, but force is given by ma from Newton's second law, and m is the mass, so it is given by the kilogram meters per second squared times the distance square, or the separation square, that's the meter square. And so this simplified, kilogram goes above, we get the per kilogram. Now meters times meter squared gives meters cube, and it goes above, it becomes per meter cube. And so we get the second squared, second is squared above, so this quantity becomes ampere squared second square. So when this second per second squared goes above, it multiplies up with that second and it becomes seconds to the power 4, and we have ampere square. So this is the base unit of epsilon naught. Now we are going to replace all these units in our equation in order for us to verify if the unit of the left hand side is equal to the unit of the right hand side. So let's get that. Now the units of the right hand side will be equal to, so let's begin the substitution. It begins with v squared. So what's the unit of v squared? V squared is given by the kilogram square we have the kilogram squared meters to the 4 seconds to the negative 6 times ampere to the negative 2. So that's the unit of v squared. So v squared will multiply epsilon a times epsilon naught. So we are going to have times the unit of the area is the meter squared times the unit of epsilon naught, which is per kilogram per meter cube seconds to the 4 ampere square. So all of this is divided by the unit of 2d, but 2 is a dimensionless constant, and so the unit of d is the meter. Now let's do some cancellations and some simplifications. So kilogram squared times per kilogram, from the laws of indices we get 2 minus 1, so this simply gives the kilogram. Now meters to the 4 times meter squared gives meters to the 6. Now this meters to the 6 minus 3, that's 6 minus 3 will give 3, so that will be the meters cube above simplified. Now divided by the meters which is below will give meter square. The next we have the second, so I have seconds to the negative 6 times seconds to the 4, so that will be seconds to the negative 6 plus 4, which is seconds to the negative 2. So we get it here, seconds to the negative 2, and then per ampere squared times the ampere we cancel, and so we finally get our unit to be kilogram meter square per second squared, which is the same as the unit of the energy that we obtained above. So it means that this equation is homogeneous. So how then do we conclude? We say since the units of the left hand side, which is E, is equal to the unit of the right hand side, which is v squared a epsilon naught divided by 2d, hence the equation is homogeneous. As required. Okay, now let's proceed with 2016. 2016 says, explain why the homogeneity of a physical equation is not a sufficient condition for the correctness of the physical equation. So it is simply because of the presence or absence of dimensionless constants. And also the method of homogeneity physical equations is not able to tell us if trig functions such as sine, cosines, tangents, or logarithmic or exponential functions are present in a given equation, since all of them are unitless. So those are some various reasons why homogeneity of a physical equation is not a sufficient condition to explain the correctness. So another typical example, you have F is equal to ma, which is Newton's second law, and F is equal to 5 ma. So we see that this is actually a force. Yes, it is definitely homogeneous, but this is not physically correct because of the presence of 5. And this is physically wrong. Sorry, this is physically correct because it respects the norms of the Newton's second law, which is the rate of change of momentum. And so that's two reasons. So you can have the presence of absence of dimensionless constants. It does not give you information if you have a trig function, exponential function, or logarithmic functions in a given equation. So those are some possible reasons. Now let's go to question B. Faraday's law may be stated in the form of E is equal to negative L di on dt, where E is the induced EMF, L is the inductance of the coil, and E and the I on dt is the rate of change of current. Determine the base unit of L. if the equation is homogeneous. So in this case, the assumption is that the equation is homogeneous. So definitely it means that the units of the left hand side, so it already means the units of left hand side is equal to the units of right hand side. So that's what it means. And so the negative sign in front of this E is equal to the negative L the I on the T. So this negative sign is a dimensionless constant, so we can take it out of play. So what we get here is, let's make L the subject, so inductance will be E times dt divided by di. So dt is simply an interval of time, and di is simply a certain amount of current that flows in that time interval. And so we can get the base units of dt. So the units of dt is simply the seconds. Likewise, the units of di, which is current, is simply the ampere. So we can now deduce the unit of E. Now E is the EMF, which is also measured in volts. So we can still use the expression the work done per unit charge, which is MAD divided by ampere second, also divided by IT. And we know that the unit of energy is a kilogram meter squared per second squared divided by the ampere second. And so we easily get the unit of potential of the EMF to be the kilogram meter squared per second cube per ampere. So that's the unit that we obtained above in 2017. So it's the same unit actually. So it means that you see that EMF, the unit, since the unit of EMF is the volts, the unit of potential difference is the volts, they all have the same unit. So in dimensional analysis, you can use the same expressions to get their respective base units. Now let's get the unit of L. So the units of L will be equal to the unit of E times dt on the I. So E has units kilogram meter squared per second cube per ampere times dt, which is measured in seconds per ampere. So it means the unit of inductance is equivalent to the kilogram meter square per second cube. Second cube times second gives per second squared times ampere to the -2. So that's the base unit, and this base unit defines what we call the Henry, capital H. So that's the units of inductance. Okay, so let's see June 2015. The first part says what is a homogeneous equation. So let's define a homogeneous equation. A homogeneous equation is an equation in which all the additive terms in that equation have the same base units. So in other words, let's see what it means. So a homogeneous equation is an equation in which all the additive terms of the equation have the same units. So we can say that is the units of the left hand side of the equation should be equal to the units right hand side of the equation. So I love most importantly this term additive terms. So additive terms is very important to note. So it makes us to understand that every term in a given equation should have the same unit, because we cannot sum one cocoyam and 2 apples, so it's impossible. 1 cocoyam plus 2 apples we cannot say is equal to 2 apples. So in order for us to sum terms in a given equation, we have to make sure that they have the same base unit. And so that's the definition of a homogeneous equation. Now what we see next is the equation P plus H rho G plus rho V squared is equal to K is homogeneous, where P is the pressure, H is the depth, and G is the acceleration due to gravity. Rho is the density and V is the velocity, and K is a constant. Determine the base unit of K. So this equation is actually known as the Bernoulli's flow equation. So it is actually defined as the mass, the energy per unit volume, this equation which we see. And though the equation is not actually correct, so it's not actually physically correct, because the kinetic part of it carries a half in front. And so if it is a homogeneous, let's verify the base unit of K. So what we get from here is we have, since a homogeneous equation is an equation in which all the additive terms of the equation have the same unit, it means the units of P should be equal to the units of P should be equal to the units of H rho G, which should be equal to the units of rho V squared, which is equal to the units of K. So simply choose one and work with. So this means that the units of P should be equal to the units of K. So what does it now mean? So it means K has units, the units of P, and P is pressure, which is the force per unit area, which is mass times acceleration divided by area. So mass is the kilogram, acceleration meters per second squared divided by meter squared. And so the units of K, therefore the units of K will be equal to the kilogram per meter per second squared. So that's the base unit of K. Okay, so now the resonance frequency F of an inductor capacitor circuit, that's an LC, is given by the equation Fr is equal to 1 on 2 pi the square root of LC, where L and C are respectively the inductance and capacitance of the circuit. Roman 1 showed that this equation is homogeneous, and Roman 2 showed that calculate the inductance of the circuit if the resonance frequency is 10 to the 4 Hz across the circuit of capacitance 4 times 10 to the negative 9 farads. Okay, so let's begin with the first part, Roman 1. So in order for us to show that it is homogeneous, it suffices for us to show that the units of the resonance frequency Fr is equal to the units of 1 divided by 2 pi times the square root of LC. Now this is the thing that we have to prove. Now let's begin with the units of the left hand side. It's easier. Now the units of F frequency is measured in Hertz, and it is given by 1 divided by the period, which is 1 all over the seconds, which is the per second. Now let's verify the units of the right hand side. So we observe 2 pi on the right hand side. It means that 2 pi is a dimensionless constant, so we care less about it. Now we are looking for the units of the right hand side. Now for the right hand side, we have 1 divided by the square root of LC. So it means our main aim is for us to check the units of the inductance and the capacitance. So in the recent sessions of this video, we saw the unit of inductance, which is far above 2015, I think it was 2015, where we saw the units. Yes, this 2016, we saw the units of inductance, and this is it in Henrys. So now, what if we didn't solve that session and you were confronted with this problem? So you have several equations which you can use in order for you to get this, and I'm going to give the easiest. So we can use the energy stored in an inductor is simply given by a half Li squared, where I is the current and L is the inductance. So it is easier to use this since we know the base unit of energy, and energy is mass, which is the kilogram meter squared per second squared. So this will be equal to Li squared, but the unit of I is the ampere, so that will be the ampere square. So definitely it means the unit of the inductance is the kilogram meter squared per second squared, and if I divide also by ampere squared, we get per ampere squared. So likewise, let's also get the unit of capacitance. Now the capacitance of a capacitor, we can get it using several ways also. So there are several ways in which we can use. So we have the capacitance of a capacitor C. We can get it from the energy stored in a capacitor, which is a half CV squared. We can get it from the definition of capacitance, where Q is equal to CV. So any equation which you feel at ease to use. So let's use Q is equal to CV, where Q is the charge, C is the capacitance, and V is the voltage across the plates of the capacitor. So this means the unit of C will simply be equal to the unit of Q divided by the unit of V. The Q is IT divided by V is work done per unit charge. So we can write it down, work done per unit charge. So the charge will come above, and so we see that the units of work done here is MAD, that's MAD times another IT. So what do you observe? IT times IT is IT all squared, and the unit of IT is simply the ampere second, all of that squared divided by the kilogram meter squared per second square. And so the unit of capacitance, so it means the units of C is equal to the per kilogram goes, we have meter squared is alone, so it goes up, it becomes per meter squared. Seconds goes up and multiplied with second squared, we get second to the 4 ampere squared. So now let's verify the unit of 1 divided by the square root of LC. So what is it going to give us? So this is the same as 1 divided by the square root of LC, that's LC raised to the power a half. And so this will give us 1 divided by inductance is measured in kilogram meter squared. Inductance is a kilogram meter squared per second squared per ampere square. And so capacitance, that will be all of this times capacitance, which is the per kilogram per meter square seconds to the 4 ampere square. So let me adjust this line. Okay, so it is 1 divided by all of this, but note all of this is raised to the power half. So in other words, the square root of it. So what we get is, this is the same as 1 divided by, so let's simplify. So this kilogram we cancel with the per kilogram, meter squared cancel with meter squared, ampere squared we cancel with ampere per ampere square and also compare ampere squared. So you are left with seconds to the minus 2 times seconds to the 4, and from indices will be s to the negative 2 plus 4, which is s squared. And so I am left with s squared raised to the power a half, which is simply 1 divided by the second. So is it the same as the unit of frequency? Yes. So we see that that unit is the same as the base unit of frequency, and so it means that that equation is homogeneous. So since the units of the left hand side is equal to the unit of the right hand side, hence the equation is homogeneous. Equation is homogeneous. Okay, now let's proceed to the B part. The B part says calculate So the B part says you should calculate the inductance of the circuit if the resonance frequency is 10 to the 4 Hz across the circuit of capacitance 4 times 10 to the negative 9 farads. Now the resonance frequency is given by 1 divided by 2 pi times the square root of LC. So squaring both sides, we get the resonance frequency, all of that squared is 1 divided by 4 pi squared times LC. So the aim here is to calculate the inductance. So making L the subject, L will be equal to 1 divided by 4 pi squared FR squared times C. Okay, now let's do the numerical application. So the numerical application is gives the inductance L will be 1 divided by 4 pi squared times the resonance frequency is 10 to the power 4 Hz, all of that squared, times the capacitance, which is 4 times 10 to the negative 9. And so let's simplify this expression and get the correct answer. Okay, so we get it gives us the inductance to be 0.0633, so henries. Okay, so in other words, it is 63.3 millihenries. So that's the inductance of the inductor. Okay, so let's get to 2013. It is the equation RT is equal to R naught into 1 plus alpha T plus beta T squared, where alpha and beta are constants. Describe the variation of the resistance of a wire with temperature T. This equation is homogeneous. Explain the meaning of the underlying word. What are the units of alpha T and beta T? Roman 2. What are the units of alpha and beta? So the first thing we have to do is the equation is homogeneous, that's the assumption. So we just know that the units of the left hand side is equal to the units of the right hand side. And so what we do is, in order for us to explain the underlying word, so a homogeneous equation is simply an equation in which all the additive terms in the equation have the same units, that is the units of the left hand side is equal to the units of the right hand side. And so for the second part, we are looking for the units of alpha t and beta t squared. And so since the equation is homogeneous, dividing also by r naught, so we have a ratio of resistances will be equal to 1 plus alpha t plus beta t squared. And so what we observe is the unit of the resistance is in ohm. So unit of RT is in ohms, which is the same as the unit of R naught. And so we get the ohm divided by the ohm, which actually gives us 1. So it means the right hand side or the left hand side is unitless. And so what then do we conclude? So since it is unitless, we have to note that the units of all the additive terms are the same. So it means the unit of alpha t is equal to the unit of beta t squared, which is equal to the unit of 1, which is the unit of RT divided by R naught. So what do we conclude? It means that the unit of alpha t is simply 1, and the unit of beta t squared is equal to 1. So it means they are all dimensionless. So what does it mean? We can just say that alpha t and beta t are, or beta t squared are unitless. Now the third part says what are the units of alpha and beta. So since the product of these units alpha t gives 1, so we now get that the units of alpha will be equal to the unit of 1 divided by capital T. But capital T is the temperature which is measured in Kelvin, so it's 1 over K, which gives the per Kelvin. And also same for, since we are looking for the unit of beta from beta t squared, so we get that the unit of beta t squared is equal to 1. So it means the unit of beta will be equal to the unit of 1 divided by capital T squared, which is 1 divided by the Kelvin squared, which is equal to the per Kelvin squared. So those are the respective units of alpha and beta. So therefore the units of alpha is equal to 1 all over Kelvin, and the units of beta is equal to 1 divided by Kelvin squared. Okay, so let's see 2011. So explain the fact that homogeneity of physical equation is not a sufficient condition for the correctness of an equation. Okay, so it's simply due to the presence of absence of dimensionless constants, and it does also give information about if you have trigonometric ratios in a given equation, or even logarithmic or exponentials. Now the B part is the electric field intensity E acting on a point charge Q placed from a test charge in a vacuum can be expressed as E is equal to KQ is equal to Q divided by 4 pi epsilon naught R squared, where epsilon naught is the permittivity of the vacuum. Show that this equation is homogeneous. So to verify if it is homogeneous, we have to get the unit of, we have to show that the unit of E is equal to the unit of Q divided by 4 pi epsilon 0 R squared. So it means let's begin with the left hand side. So let's start with the left hand side. So the unit of the electric field strength E. So the electric field strength is simply the force per unit charge experienced by a point charge. Okay, so we get that the force is MA, so that's a kilogram meter per second squared divided by unit of charge, which is IT, that's the amp per second. And so it's simply the kilogram meter per second cube per ampere. So that's the unit of the left hand side. And so now the unit of the right hand side. Let's deal with the right hand side. So the right hand side, we have the unit of charge. The units of pure is the ampere second. Now unit of epsilon naught. Units of epsilon naught is equal to. So we can get the units of epsilon naught from Coulomb's law of electrostatics, or also from the equation c squared mu naught epsilon naught is equal to 1. So here we can also get the value, the base unit of epsilon naught. So there are several ways which you can get that value, but we are going to use the Newton's law of the Coulomb's law of electrostatics. So it says that the force between two charges Q1 and Q2 is given by the expression F is equal to Q1 Q2 times 4 pi epsilon naught r squared. And so from here we can get the base unit of epsilon naught to be equal to Q1 Q2 divided by 4 pi f r squared. But the 4 pi is dimensionless constant. So this means the unit of epsilon naught will be equal to the ampere second, all that squared, divided by the force, which is kilogram meter squared per second squared, times the separation, that's meter squared. So we get ampere squared second squared divided by kilogram meters to the 4 per second squared. So this gives sorry about that, this is meters. Meters times meter squared gives meters cubed. Okay, so what we get from here is we get the final base units of epsilon naught to be per kilogram per meter cube seconds to the 4 ampere square. And so we replace inside our equation. So R is the separation of the charges. So this is the unit of epsilon naught. Now the unit of R is simply the meter, and so it means that the units of R squared will be equal to the meter squared. Okay. So this means that the unit of the right hand side in total will be equal to Q, which is the ampere second. Let's use another ink. So we are going to get the ampere second. So it means the units of the right hand side will be equal to Q, the units of Q, which is the ampere second, divided by 4 pi epsilon naught. The units of epsilon naught is per kilogram per meter cube seconds to the 4 ampere square. So this multiplies the distance, the square of the distance, r squared. And so let's do some simplifications. So we get that the ampere simplifies with one of these ampere, and so the kilogram goes above. We get kilogram. Negative 3 plus 2 is negative 1, so when it goes above it becomes 1, and second here 1, second goes above it becomes per second cube, and the ampere becomes per ampere. So we will find out the units instead of A. Now, so we get the kilogram meter per second cube per ampere, and this gives the kilogram meter per second cube per ampere. So we see that the two units are equivalent. So this unit, kilogram meter per second cube per ampere, which is equivalent to this other unit. So we conclude, since the unit of left hand side is equal to the unit of right hand side, then our equation is homogeneous. Okay, so let's get the last question of this video. So we have the force per unit length F between two wires placed at a distance r apart in a vacuum and varying current I1 and I2 in the same direction given by F is equal to mu naught I1 I2 all over 2 pi r, where mu naught is the permeability of a vacuum. Show that this equation is homogeneous. So one thing we have to realize is F is not the force, it is the force per unit length. And so we get that we are going to use to find it for us to show that the unit of capital F is equal to the units of mu naught I1 I2 all of this divided by 2 pi r. And so what we get from here is we are going to let a certain small f change variables f to be equal to capital F. Okay, where small f is the force. Sorry, we are going to let capital F rather. We are going to let capital F to be small f all over L, where f is the force per unit length. So it means the units of capital F will simply be the units of small f on L, but here F is the force and L is the length. So that's the force per unit length, and so the units of force is kilogram meter per second squared, this divided by the meter, and so we have the kilogram per second squared as units. Now let's get the unit of the right hand side. So in order for us to get the unit of mu naught first, so let's start with simple units. So for the right hand side we have the units, we have to find the units of mu naught I1 I2 divided by 2 pi r, but 2 pi is a dimensionless constant, so we care less about it here. And so we have the units of I1 is the same as the units of I2, which is actually the ampere, and so the units of R, which is separation, is the meter, and so the unit of mu naught. So we can use the definition of the magnetic field, which is mu naught I divided by 2 pi r, and so B is the force per unit current length. At times, to avoid just going back through the same equation, we can use other relationships. So also the Lorentz force is given by dqv, where q is the charge and v is the speed, and so we get that the base unit of v is the force divided by the charge times the speed. So this means we can use either this relation or this relation, sometimes avoiding to turn back around, since we can use this to come out with the initial equation. So to avoid turning around, we can use an expression that is different, and so we get that B can be replaced by F, the units of F divided by the units of QV, which is mu naught I all over 2 pi r. So that 2 pi is a dimensionless constant, so making mu naught the subject, this means the units of mu naught will simply be equal to the units of Fr divided by QV all of that times I, and so it means the unit of mu naught will be equal to kilogram meter per second squared times displacement meters divided by charge ampere second times speed is meters per second and current is the ampere. So let's get some cancellations. So following some cancellations, we get this meter cancels with this meter, and so the expression of mu naught simplifies to a kilogram meter per second, amperes. This per second and this per second the seconds and the per second cancel, so this remains per second squared per ampere squared. Okay, and so let's replace this now in the expression of the right hand side. So the expression of the right hand side, it's simply mu naught I1 I2 all over 2 pi r. So the units of the right hand side will be equal to mu naught, which is the kilogram meter per second squared per ampere squared. So we are multiplying by I1 I2. So I1 has unit ampere, I2 has unit amperes, and so it becomes ampere squared. All of this divided by 2 pi r meters, and so cancellation occurs. Second squared, ampere squared and per ampere squared cancels, meters and meters cancel, and so we are left with kilogram per second squared. Now verifying with the unit of the right hand side, of the left hand side, we have the kilogram. So we have the kilogram per second squared, which is the same as the kilogram per second squared. So we see that both units of the unit of the left hand side is equal to the unit of the right hand side, and so since they are all the same, it means that that equation is homogeneous, and that's a proof. So this brings us to the end of this video. Thank you so much for watching, and please do not forget to like, share and subscribe. See you in our next video.